I'll give you a tip. I'll give you a tip.
Okay.
When you test your H2, the only way, not the only way, one way to say that it is H2 is to put a magnet against it and see if it moves with the magnet.
Okay. And should it move?
And if it is moved, you got your H2.
Okay, then we got our H2.
Congratulations.
Yeah.
The way to do it, I tell you, these are the test development. We share knowledge in so many ways. If you made a H2 and it's in black color, as we said before all the time from the beginning, the reason for it being black is H2 in so many ways is a plasmatic condition, and in a plasmatic condition, due to its orientation, becomes carbon-6 to make a full sphere, or what we call hexagonal shape of itself. In when you put magnetic fields together, this is the natural process when there's layer of them. So in that process, when it's a carbon, if you understand the composition of parameters of the carbon magnetic field, you will find out it leads to creation of behavior as a plasmatic condition of iron in a bigger structure. So it behaves like a magnetic, but in fact is deuterium. And the way to understand, and when it says is you can use it with a magnet and use it if it moves, get yourself nanocoat 2 magnets and place it in the salt and put your deuterium in it. And as usual, you're trying to make a GANs of, you think, the what you call magnets, but just connect the 2 magnets with the wire to each other and leave it. Connect the 2 wires to a load, which is a very small load, and then leave it. And what you observe is that the black stuff becomes pinkish. It becomes hydrogen. In a condition of magnetic field, or it becomes tritium. It changes pink. You might still see some black residual which comes from the creation of the what you call CH3, because if we go back to the CH3, this is a lot of people asking how we get a confirmation, and I know John is onto this as well. It's very simple, as I can draw it for you, is you got to understand at the beginning of the production of the what you call CH3, what you do, you put nano-coated copper, Na, and then you put what we call composite coating, which is the zinc and iron. So if you, in fact, you look at it, you are working on a very typical condition that, I'll better strengthen this because I don't see that way. You have the zinc coating, and then behind it you have the iron coating, iron inside it, because it's galvanized the steel. So what you got to look at in a scientific way about it is very much you have 2 processes going at the same time. You have this process, which is the zinc and the what you call the nano-coated copper, and then you have a second process which is between the iron and the zinc, sorry, the copper. So these 2 processes create its own condition. This gives you the CO2 which you have created, which on the other hand, the iron and this gives you here, the difference in the first one is 56 to 60. Yeah. And in the other one is the zinc, which is the usual 6. Here is the copper and the iron take place. In the isotopes of it is more or less just only 3. That's why you get the CH3 in the balance of the energy. So that's where the H comes from. So when in that process you go through isotopes, then you find out partially when the zinc balance goes away, when the coating of the what you call the galvanized plate goes, now you're only dealing with H3. But because the carbon balance of the zinc is more or less um, eradicated, is used for production of the CH3, now the only thing is left is H2, because the zinc is not there, and the carbon condition between the zinc and the copper nano-coated does not exist. So in fact what you have a copper nano-coated condition with CO about 60, 59, 60, and you have a what they call the iron on its own. So it's a very, very small gap. The only thing left, the majority, is giving you H2. Because the balance of the interference between the two, if you go towards 57, 58, towards 60, 59, H2 is a more powerful, balanced, stable, and that's the H2 is created. But immediately it changes itself into the condition of, because has the presence of the iron to the what we call the isotopes of the spherical condition dynamic, which creates and absorbs the magnetic field of the iron property. So it behaves like an iron and interacts with magnetic field. This brings a lot of knowledge in the background in the world of science. And if you go back from the beginning, some months ago when I started teaching you, I always told you deuterium is black. And now if you test it, you confirm it. And if you use the energetic fields, you'll see it changes to pink, or what they call it, to orangish color, which is the H3. Because if it was a pure iron nano material, what you're going to be left with is iron, and it shouldn't change color. But when it changes to H3, if you put a magnet on it, you see it doesn't move. It has the property of H3. This is one way of confirming what you produce is deuterium for your space fuel.
Okay,
and it goes in line with what we have